Good morning, everybody, and welcome to my Probability and Statistics Math 3350 course. Looking forward to a good summer. Hope you are too. A couple of things that we need to accomplish today. First of all, the course uses the open source freeware software R. Costs you absolutely nothing, and it's wholly contained in the UNG Data Hub. We'll be taking a look at that. Let me just click over and show you that there are notebooks and we can actually run things in these notebooks and we can type notes in these notebooks. So R will be an addition to us, and we will generally use R during statistics because it is statistical software, but we can use it as a scientific calculator. You are allowed to have a TI-84 type graphing calculator with you, and it can be useful during the probability portion. Also, we can use R. Either one is fine. So the first thing we need to do in terms of probability is reframe all the basics that we know from high school and earlier college courses in terms of sets, right? And we're going to go through that in just a second. We also are going to review counting principles that you've probably seen, how to use factorials and combinations and permutations. And we're going to learn how to access R and use it inside the UNG Data Hub. And we're going to start to get a little bit familiar with the Data Hub and the different files that can be found there. And of course, we're going to actually do some mathematics. We will practice some probability questions as we go. Let's launch into what we need to know about sets. Okay, so basically, we're going to look at probability experiments, and that a probability experiment is an event, the outcomes of which are perfectly random, and also you can predict them exactly by probabilities. Okay? And so a probability space or sample space has a superset that covers all possible outcomes of the probability experiment. So I'm going to call that set S. Some people call that set U for the whole universe. It's the sample space of all possible outcomes. And events, probability events, are sets of outcomes. They're either a single outcome or, well, a set can be a single outcome, but or a set of multiple outcomes from that probability space. And we tend to use set notation, so we'll use a capital letter. So for example, the probability of event set A is defined to be, and oh, what's the absolute value there? So we're using the absolute value to denote, sorry, uh, my apologies for the beepings there. Okay, so the absolute value in set notation refers to the cardinality of set. The cardinality of set is just the number of things that are in the set, right? So a deck of cards has 52 cards, so that set has a cardinality of 52. We're looking at discrete probabilities right now, so that number will be finite. The cardinality of a set can, in fact, be infinite. Okay, so we're going to talk about some more things to do with sets. Why? Because we use different ways, different sets, intersections, unions to combine or recombine the event sets. And set complement, so an A with a bar over it refers to all of the outcomes that are not in the set A, right? So the complement is the elements not in A. And we'll use A bar to denote that. You'll sometimes see people use an A with a superscript C after it for a complement. A bar gets a little confusing in probability and statistics when we get to the statistics portion because we use it in a slightly different way. We use that same notation in a slightly different way. But for now, A bar means the complement of A. Unions A union B is the event either A or B. So either the outcome is in event set A or the outcome is in event set B. Okay, and the probability of A union B, right, is the probability that the outcome is either an event set A or an event set B. Intersections, both A and B. This is different than repeated trials where we do first A and then B. Those are slightly different formulations, and we'll see plenty of examples of both. I don't think this will be confusing going forward. It may be a tad confusing at the moment. Set subtraction, we don't use this a ton, but just so you know, we do use A minus B to refer to A intersect B complement. And we say A throw away B because that's essentially what's happening. You know, you have this this intersection of A intersect B, that piece gets thrown away from A. So A throw away B is how we refer to that. Not terribly important. What is more important is as we go forward, and again, this is an introduction, so I'm going to review a lot of things you've probably seen. All right, but I want to focus you on the kinds of things that we're looking at when we do probability problem solving, things that become important because they guide us into which tools we'd like to use. So the first thing we want to think about is when we have repeated draws or repeated trials. Repeated draws, like for example, you're getting dealt a 5-card poker hand from a standard 52-card deck. Okay, well, that's 5 repeated draws. Repeated trials, that's like a coin flip, right? So I'm going to flip a fair coin 10 times, and how many times does it comes up heads? So when we have repeated draws or repeated trials, we need to know whether those draws are with replacement, like with the cards. Excuse me, I'm sorry, like with the coin, right? If you flip a coin or you roll a die, you can still get heads or tails the second time. Or if you roll a 3 on your die, you can still get a 3 the second time you roll the die. So that is with replacement. The outcomes are replaced into the superset. Draws without replacement are like the poker hand, right? Because if my opponent gets dealt the ace of spades, then I cannot also get the ace of spades. Once the ace of spades has been dealt, it does not get replaced back into the deck, back into the sample space. So with repeated trials, when we rerun the exact same experiment several times, like roll a fair die 20 times, flip a coin 5 times, those are repeated trials, right? The exact same experiment is being conducted over and over. We have a name for this because we do it a lot, and the scenario is called Bernoulli trials, and it has a lot to do with the binomial theorem. So I'll leave it there. It's a big it's a big area. It's not that complicated, but there's a lot of content in that area. So I'm going to leave that summary alone there. Also, one thing that we're going to learn going forward is the idea of independence. When the probability of A and the probability of B occurring are independent of each other, that means A happens with the same probability whether B has happened or not. Or the same in the reverse, B is independent of A if B happens at the same probability whether A happens or A does not happen. Okay, so we'll learn how to calculate that, determine when probability events are independent, and it'll be important to us. Also, the order matters, as most people know. I'm assuming this is review that combinations are when order doesn't matter, and permutations are when order does matter. So if we're spelling words, and by the way, when I say spelling words from the letters using Mississippi, I mean things like SMI, just any 3 letters that you pick from the letters in Mississippi is a word. So kind of word with scare quotes, right? When we draw words from a certain number of letters, we don't mean that they'll actually be in the dictionary. But if we're drawing letters, SMI is different than ISM, right? So the order does matter. The order drawn does matter. It doesn't matter when I'm getting a 5-card poker hand if I get an 8, whether that 8 comes into my hand first or comes into my hand last. When we go to showdown in poker, that card counts the same no matter when it was dealt to me. So order doesn't matter. So we use permutations for the letters in Mississippi, and we use combinations when we're talking about drawing a 5-card poker hand or similar. And let's take a look. This is the course website, and I'm scrolling back to the top of the first page, and there is a nice table of contents, right? But we're just here at the main page, and there's some really good stuff. The teaching notebooks we have are not exactly the same. Clearly, they're similar because we'll have some formulas in the online course notes that will also appear in certain places in our course notebooks. Okay, so this is the link I provided to Probability Unit 1. This is an R notebook that we'll be using in the Jupyter Hub, and it comes to you and it has some notes. It also has some links to the two sections in the book that we'll be interested in looking at. We're actually going to use this R calculations and factorials in just a second. Why? Well, because R has a factorial function, but for permutations and combinations, we have to write our own functions, which I have provided here. You can copy them right out of the notes, and I've given you the link right there. Some of this information, again, you've seen already, and the features of probability experiments that we talked about. And we'll get down here to using R for scientific calculations in just a second. Okay, so efficient counting, what operations are involved in the probability formula? Probability of A equals the cardinality of A over the cardinality of the sample space, right? The total number of outcomes in the event set divided by the total number of possible outcomes. So we do need to be efficient at counting. We need to have a lot of quick ways to count different things up. Now, one of the things we do is repeated trials of exactly the same experiment. We can multiply, right? If we flip a coin 3 times, how many possible outcomes are in the probability space? Well, there are 2 outcomes possible the first time and then 2 more the second time. So it's 2 times 2 times 2, or 2 to the third, right? So 2 to the third. Oh, sorry. There we go. Permutation, if we arrange 8 books on a shelf, how many possible outcomes are there in the probability space? And a 5-card poker hand, how many different poker hands are there? Let's take a look at the permutations where we arrange 8 books into 5 slots on the shelf. So in other words, we don't have room for all 8 books. We can only choose 5, but we can put the 5 books down in any order. So how many possible arrangements are in this probability space? And the answer is 8 permute 5, right? We have 8 books to permute into 5 slots. You know, this might be the same. You might see it as there are 10 students in the hallway and 5 come in to sit in the classroom, right? And then we might have 30 chairs in the classroom. So how many different arrangements are possible? Well, 30 permute 5, which is a large, large number. All right. And the permutation formula, if we are, and I'm sorry, permutation, that should be ordered. My bad. Let me highlight that for you, right? This is ordered. The number of distinct ordered arrangements of n objects into k slots is n factorial. I don't like this. This was a copy paste error. That's the combinations formula. Dang it. So if we're doing n objects permuted into k slots, it's equal to n factorial over n minus k factorial. So this is the correct formula. Sorry about the confusion there. Let me get rid of all the scribbles on the page. And how many combinations, how many different poker hands are there? Well, some of you may have seen this notation. We call this 52 choose 5. That's how we read it. And it's the binomial coefficients. They come from the binomial theorem, the coefficients that we find in the binomial theorem. But they're also the number of ways that I can choose a certain number of things, k objects from n, where order doesn't matter. So this is correct. And finally, now we see the formula in its correct form. And I feel badly about having the formula incorrect on the previous page. Sorry about that. Okay, let me jump into the to the notebook, the teaching notebook that we have. Again, I'm not going to go through every single thing. Oh wait, this is the sorry. This is our teaching notebook. Got it? Okay, so a couple of things about the data hub. If you hit Shift Enter, it evaluates the cell and moves down. And notice that these cells are markdown cells. We do have code cells when we want to use it as a calculator, and that's something to know. Set complements, these are still all markdown cells, and here we get to a code cell. Notice it says code right here. And when I do factorial 7, I get 5,040. Remember that 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. So factorial is in native R. Sadly, combinations and permutations are not functions they've given to us in native R. So we write functions ourselves. Okay? And if you want to look at the code, you'll see that these functions do in fact match what we said. And it turns out that you can just take the combination formula and multiply by factorial k to get the permutations of n objects into k slots. So those calculations are correct. And just to test them real quick, we have combination 7 choose 3, and that's 35. Why? Well, that's 7 factorial over 3 factorial times 4 factorial, which is 7 times 6 times 5 divided by 6, which is 7 times 5, which is 35. If you didn't follow that calculation I spit out there, there is some more. The formulas are here, and they are correct for combinations and permutations. Okay, so that's why I provided this link. If you aren't familiar with that, 7 permute 3 is 7 minus 3 factorial, 7 factorial divided by 7 minus 3 factorial, which is 7 times 6 times 5, which is 7 times 30, which is 210. And again, check that link if you don't know, though. That is something that we are going to have to be able to do. Okay? And we talked about this already when we did it on the PowerPoint. If we flip a coin 3 times, how many possible outcomes are in the probability space? Well, we should know that that's 2 to the third. I'm typing in 2 caret third and hitting Shift Enter. Shift Enter will evaluate the code and move down. I have the option to do Control Enter and it'll stay in the same place so I can reevaluate it. This will sometimes be useful when we're randomizing things. But generally speaking, we just hit Shift Enter and move down. You can also hit Run. That's perfectly fine. Shift Enter, Run, it all works. Permutation. So how many arrangements are possible? For 8 books on a shelf, I'm not doing 8 permute 5. I'm just doing 8 permute 8, which is 8 factorial. And remember, we can always just do factorial 8. And this is always cool. If you want additional cells, you can hit the plus sign, and then I hit the plus sign, and I can try this. I can do perm 8 comma 8, right? Will that work the same way? In other words, the formula we wrote for permutations, if I 8 books permute into 8 slots, you notice that they evaluate exactly the same. Okay, so combinations, how many different poker hands are there? 52 choose 5. And the reason we say 52 choose 5, it really is that, right? We have how many ways are there from 52 objects to choose 5 when order doesn't matter, right? So we can do combin 52 comma 5, Shift Enter, and there are 2.6 million poker hands. Clearly it's an integer. R has lost a little bit somewhere in rounding error. But about 2.6 million poker hands. And so next we have these practice problems that we can tackle. Okay. Please take a moment to try them. And by the way, this might be a time to pause the video and go through and see if you can calculate them. Okay, so if you'd like to, please pause the video and try some of these. And I assume now we're back. So how many distinct arrangements of the letter cat are possible? Well, it's 3 permute 3, right? Because ATC is different than ACT. So order does matter, right? So um, there are 6 different ways you can arrange those 3 letters. If a coin is flipped twice, what is the probability of getting 2 tails in a row? Well, the probability of getting the first tails is 1/2. And then the probability of getting a second tails is 1/2. But they're 2 independent trials, right? Excuse me. They're repeated trials of the exact same experiment. So we can multiply them. They are independent. Whatever the coin flip is on the first one doesn't affect what happens the second time. Okay, and I'm just, reminding you of some different ways we can use R as a calculator. If we roll 2 standard dice, what is the probability of rolling a 5? A 5 or less. Now, I'm wondering exactly what this means. I believe this is the Monopoly dice roll. Okay, so I'm just gonna the in a code cell, the hashtag is a comment, so I can say assume this is the Monopoly dice roll where we take the sum of the 2 values. Okay. So if I'm rolling 2 dice, what's the probability of rolling a 5? A 5 or less? Well, I can roll a 1 and 4, a 1 and 3, a 1 and 2, a 2 and 3, 2 and 2, 2 and 1, right? So I'll let you think about that. Probability of rolling a 5 is 4/36, right? I'll have to think about that. And I have a nice way to show that that I can't draw in this space. So let me jump on as you're thinking about that one. If we draw a card at random from a standard deck of cards, what is the probability that we choose a heart? Okay, so again, the probability of a heart. What's this calculation? Well, it's just 1/4, right? Because in a deck of cards, we have 13 cards of 4 different suits. So 52 total cards. We have 13 spades, 13 hearts, 13 clubs, and 13 diamonds. If you're not familiar with the deck of cards, notice that this probability playground, which is the second section of the book, it goes over everything in the card, and in a standard deck of cards, including color and rank or value. And then this is a way that we often display these. So there's a lot of information here about how to deal with this probability playground. And why do I continue to use card examples? Because it is a deck of cards allows us to have examples for nearly every type of situation that we see in this course in terms of probability. Okay, but the probability of a heart is 13 over 52, right? Which does in fact reduce to 1/4. How many 3-digit numbers are there that are strictly less than 600? And you'll have to give me what you think about, is that a 3-digit number? Because if that's a 3-digit number, then there are 599 3-digit numbers that are strictly less than 600 if we don't allow negatives. But then the question is 0, 0, 0, 0? I would say that the answer here is 599. Again, on a test, I might have to make this a little more specific so it's really, really clear exactly what 3-digit numbers we're allowing. But here we are allowing 001, 002, and for 11, 011, for 28, 028, right? But if we allow those as 3-digit numbers, There are 599 three-digit numbers less than 600. If you only allow three-digit numbers and a number like 28 doesn't count as a three-digit number, this changes, right? And you should think about how that changes. How does that change anything? Well, the smallest three-digit number is 100. So all the numbers between 100 and 599, that would be 499, right? So again, I'll have to be pretty specific if I ask this on a quiz or a test, but I hope you understood the explanation for both of those. In base 6, how many different base 10 three-digit numbers are there? Right. So base 6 are numbers like this, and we often put a little superscript there, 6, to let you know that it's in base 6. But in base 6, we can only use in base 10, we use the digits 0 through 9, right? So in base 6, we use the digits 0 through 5. Okay. And if we have three digits, right? And we have six choices for any of the three, because right, this kind of thing is perfectly fine. 335 is a basic number with three digits. So if I have three digits and six choices, right, for each one, then I have 729. And that's why the base 10 is here in parentheses. This calculation has to be done in base 10, even though we're talking about base 6. Okay. And again, we're allowing 0 to be one of the numbers. Okay, how many license plates are possible if they're three letters followed by four numbers? So we have something like A, B, C, 7154. Okay, and this is pretty similar to Georgia license plates, but how many of them are possible? Okay, any letter or number can repeat. We just have to have letters first and then numbers. So I have 26 three times. Three times I'm choosing from 26 letters. You know how license plates are, they don't have lowercase. So there's only 26. If you are allowed lowercase and uppercase, then that would be 52. But we only have 26 options. And then here for the numbers, we have 10 options each time and four numbers that we're drawing. So this is where we're drawing with replacement, and we can use powers to determine that there are, and I have to see how many, that's 175,760,000. Okay. If we draw two cards at random from a standard deck of cards, what is the probability that both are hearts? Okay. So this is a little more complicated than you think. But what I'm going to do is I'm going to find not the probability of heart and then heart. I'm going to do it with combinations and do it all at once. And the probability of two hearts is going to be equal to, well, what I'm doing is I'm drawing from the hearts, and there's 13 hearts, and I have to draw two of them. How many possible things are there in the sample space? 52, choose two. So I'm doing 13 choose two divided by 52 choose two, right? And the probability of drawing two hearts, if I just draw two cards, is a little less than 6%, as you can see. Okay. And if we randomly select the elements of a 2 by 2 matrix, now that means there's four elements, from the set 0, 1, what is the probability that we have a row or column of all zeros? Interesting. I'm going to leave that. That's not a particularly hard probability problem if you can solve the logic puzzle of the patterns we're looking for and how to count them. Okay, so I'm going to bring this to a close, and I will return to a couple of these that I left undone. I also want to mention that I'll be having a online help session every Thursday evening at 7 p.m. So we can go over questions on these kinds of things. Also, your notebook has exercises. These are pretty simple questions, and there are solutions to exercises. And in D2L, there's even more practice problems. And we'll have plenty of chances to talk about that in the online help sessions on Thursday evenings. All right, thanks so much. This was lesson one, and I'll see you on Wednesday with another installment.